Hello, everyone. Today we are going to continue discussing the idea of embeddings in machine learning. So previously we talked about the ideas in machine learning. So we talked about how we how we get embeddings for word, how we get embeddings for graph nodes, and how embeddings are used in the recommendation systems. And here in this lecture, we're going to talk about how to find embeddings for the whole from the embeddings like how do we find embedding for whole from the embedding for parts? For example, if we have embedding for words, how do we compose embeddings for sentence? And if we have the embedding for sentences, how do we get the embeddings for documents? So that's what we're going to talk about today. So first, let's review what we mean by embeddings and why we want to use that in machine learning. So basically, the idea embedding is to convert the item we want to learn into a vector. For example, the item could be word, could be image, or something like that. And so we want to use a vector to represent our item, and so that the vector can be processed by a machine learning models. So that's the first idea. It can be easily processed by a computer. The second thing is by using the embedding, the similar items can be projected to the same same regions in the embedding space. For example, here we have a word road, car, and also image of car. So with the embeddings, we can see that they are projected to the similar regions in the embedding space. So that's the second idea for embeddings. And we also talk about the how do we interpret embeddings for example, for words. So we can see each dimension as encoding a specific information for the word. For example, we can see that the first dimension can be like representing the whether the word is related to animal. So in this case, the cat and puppy has a very high score because they both represent the animal. And also, if we look at the third dimension, which represent humans, and we can see that the only baby has a very high score here because baby is related to human, and all other words are not related to human. So by looking at the scores for different dimensions for a specific word, we can actually get the property of this word. So that way we can basically encode the specific word using these different dimensions in word embedding space. Okay, so we also talk about how we want to train the word embeddings using the idea of word2vec. So the idea here is to use constructive learning. So it basically say that we provide the neural nets with two words, and we want to predict whether the words whether they are neighbors or not. So if they are neighbors, they should have a very high score. Otherwise, they should have very low score. So by doing this kind of contrastive learning, we can get the embeddings for words. Okay, so now let's go to the main idea for this lecture. So how do we want to form the sentence embedding if we have the word embeddings? So the one way to do that is to do simple average. For example, if we have like the embeddings for 3 words here, we can take the simple average and get a sentence embedding. So that idea is very simple, but they do not usually work. The reason is there are 2 issues we want to consider. The number one is the word order really matters. For example, if we have 2 sentences, Tom likes Jerry, and the second sentence is Jerry likes Tom, so they have different word order, but they use exactly the same word. So if we use simple average, the sentence embeddings will be exactly the same for these 2 sentences. But we know that the order really matters, so they should have very different embeddings in this case. So that's the first issue of the simple average. They do not capture information about the word order. The second thing is the word may have different embeddings in different meanings in different contexts. So, for example, if we look at these two sentences, I deposited my money at the bank versus the fisherman sat on the bank. So we can see that the word bank have different meanings in these two different sentences. The first one means that the bank is a financial institution, and the second one is the bank of the river. So that's like totally different meanings. So if we use the simple average, they do not the embedding for bank will be exactly the same, but in reality they should have different embeddings. So simple average will not work in this case. Okay, so the solution for that is instead of using the simple word embedding, we want to take the context into account to get the contextualized embeddings. So which means in this case, instead of using the embedding of word, we want to use embedding for word given the context. So why do we want to do the contextualized? Because by doing contextualized process embeddings, each word can actually see its relationship to other words, so that we can get like richer meaning for specific words. So by doing that, we can better combine these contextualized embeddings to form the sentence embedding. So this is what we want to do in the next few slides. So basically, we want to do these two steps. Number one, how do we get the contextualized word embedding? Second thing we want to consider is how do we want to combine these contextualized embeddings? Okay, so first let's consider how to find contextualized embeddings. So we are going to use three different methods. So first one is to use bidirectional GRU. So as we know that the GRU is pretty similar to LSTM, it can take care of the sequence of data and output a sequence as the hidden vector. So for example, if we look at the word the sentence consisting of L words here, so it goes from W2 word to 1 all the way to word to L. We want to have two GRU. So first GRU goes from left to right, the other one goes from right to left. That's why it's called bidirectional. So if we go from left to right, so each word can see all the words before it. And if we go from right to left, each word can see all words after it. So for example, if we look at the second word, W22, we can see that if we go from left to right, we get a hidden vector H22, which encode information from the first word and also the second word. And also, if we go from right to left, this vector H22 encodes all information for words from like W2L all the way back to W22. So if we concatenate these two vectors, then we basically get the embeddings for the second word, including all the context from left to right and right to left. So that's why we can see this concatenate vector as the contextualized embedding for this second word. Okay, so that's the first idea for getting the contextualized embeddings. The second way we can get the contextualized embedding is to pass the word embedding through a transformer. So for example, in this case, we have 4 words, and we can pass them into a transformer and then get the contextualized embedding. The reason why we can get the contextualized embedding is that the transformer, inside the transformer, will basically have an attention mechanism which will compute the attention score for each word, so that the word can attend to like its context in the sentence. So that output will be the contextualized embedding for that word, because it not only incorporates the meaning for that word, but it also incorporates the meaning for the entire context. So that's the second method. A third method to do is to basically use a existing model. For example, we can use a model called BERT. So here we pass a sentence into a BERT, and the output will be will naturally be a contextualized embedding. So that's the third method. We want to use a pre-trained model to get the contextualized embedding for words. Okay, so now that we solved the first problem, we are going to talk about the second problem, which is how we want to combine the contextualized embedding. So one way to do that is to do the average. So to do the simple average, right now we have a contextualized embeddings rather than the original simple word embeddings. So taking the average will get the reasonably good sentence embeddings in a lot of cases. So that is the best. That is the one of the way to do that. Just to take the simple average. But sometimes the simple average will not work well. So we want to use a more sophisticated way, which is to use the attention mechanism to compute the attention-based weighted average. So the idea is we want to have a attention score, which is A1 to AL here. And here we see that H1 to HL is just the contextualized embeddings for each word in a sentence. So we compute these weights, A1 to AL, and then we want to use the weighted average, which is like this, S equal to the weighted average of the hiddens of this contextualized embeddings. And each contextualized embedding, so each attention score AI is a function of a vector UW and the its own vector, its own contextualized vector HI. So we can compute the attention vector like this. So after this processing, we get the attention based weighted average, which basically means that a specific sentence can have different attention to its component words. So that way we can focus on important words and ignore some very non-important words. That could give us better results for sentence embeddings. Okay, so that's the general idea of how we get the sentence embeddings from word embeddings. And using similar ideas, we can also go from the sentence embedding to document embeddings. Just do the same thing. First, we get the contextualized embedding for sentences, and then we want to combine the contextualized embeddings for sentences to get the document embeddings. So this kind of hierarchical structure is what has been discussed in this example model called hierarchical attention network. Basically, this model is doing the two-step process. The first step is to form a sentence embedding from word embeddings, and then it forms the document embedding from sentence embeddings. And after these two processing, we get the document embeddings and the final embeddings, which will be used for classification problem. So that's the idea of the hierarchical attention network. So by doing this, they actually find that this beats the existing models at that time and achieve the state-of-the-art performance in the document classification task. Okay, so that's all for today. If you have any questions, please leave a comment. And thank you so much for your attention.